Hey guys, I'm Gabriel Charette, gab@chromium.org, yeah, this is my first time giving such a talk, and this is also the first time this talk is given, unlike yesterday's, so bear with me. I think it's pretty packed, so I'm going to go fast. Hopefully I have time for questions at the end. If not, I'll go into Dory and answer textually. So today we're going to look at everything that happens at the low level from the moment you click that little lifesaver icon at the bottom. Already, when you have a Chrome window popped, there's a lot of stuff that's already happened. The multi-threading environment's been set up. Sync might have started to do things in the background. Your bookmarks have been loaded. Maybe you even had a session restore bring up a bunch of tabs, which means your navigation stack is set up, history is up, autofill is ready to go. And then maybe you close some tabs. You're doing your navigation thing. Maybe you open another profile, and then we do all of this all over again. We load everything for the second profile. And then at some point, you get tired of it. you close your browser, and we enter into the shutdown phase, and everything goes back to disk, and we're done. So how does this work in the back? So today I'm going to dig into what happens inside of the browser process. Yesterday, this is a slide from Jam's Anatomy of a Browser, which hopefully you attended. So we have a multi-process architecture. I'm going to go into what happens inside of the browser process. Other processes are similar, kind of simpler perhaps, because they don't have to worry about disk I/O and so on. Here's the anatomy of a browser process. You don't have to squint at the left-hand side. I'm going to go into explaining a bit what this means. This is a very tight view of a Chrome trace. So if you go in Chrome://tracing, you can trace effectively what's happening on all the threads. And this is a view of the browser process in a random point at runtime. Here we have the main thread in the middle, also known as browser thread UI. This is where system events are going to be coming in for input. And this is where the core of the work in Chrome, if you will, is happening in the browser process. This is where we process the services are living and so on. We also have the I/O thread, the communication thread. Again, the I/O thread is a place where you're not allowed to do file I/O, which is kind of confusing. This is where net and IPC mainly are happening. We also have all of the TaskScheduler workers. These base TaskScheduler is where you can post async work to every process. In fact, we have TaskScheduler workers in every process. You can use the TaskScheduler API to post tasks to the worker pool, and then we have a bunch of workers picking up that work. We have background workers, workers meant to do file I/O only, so they don't interfere with the workers doing CPU work, and so on. And you also see in the top there, we have history threads, sync threads. Those are old pre-TaskScheduler threads. Hopefully they go away pretty soon. Don't worry about them. They just haven't been migrated yet for legacy reasons. Again, other processes are similar. Yesterday in Life of a Pixel, we saw what's happening in the renderer. I'm not going to go into those details. So how do we get to that stage with all of those threads running? This is a trace of Chrome startups, and we can't see at the bottom right here, but with Chrome exe -- trace startup, you can actually get a startup trace and Chrome tracing, which you can load after. So first thing we do is we enter browser main. And in fact, this is not the first thing, because if you look on the left-hand side there, there's a bit of things that have happened already. I apologize, the screen resolution is not really good. So here we loaded, actually, on the left-hand side, this is loading the exe, the DLLs. And right after that, we enter browser main. And eventually, we reach steady state, also known as run loop run, where, like I said, things are running. And this is the simple part. So today, we're going to look at what's happening in the middle, in the startup phase there, where everything is not quite initialized, and how we go in the order of everything. In a startup trace, you also get nice events there, which are reported through UMA and metrics. So for example, here we have the first paint, the mainframe load. These are events. Yesterday, we looked at the navigation stack. So when the first tab is loaded, we send an event, and we say, we're done loading the first paint. We have UMA. This is how we optimize startup. Let's dig into startup. First thing that happens is browser main loop, early initialization. So this is where we create the scheduler. This means that we're creating the queues. We accept tasks. We're not yet running anything. but we accept tasks in our queues. We read the local state file. Local state is a file where the basic preferences of the browser are saved. So we have your profile list. We know which profile was the last one you used. You know how when you load Chrome, it always loads your last profile. This is where it's saved. We know which field trials we should run. So field trials, also known as Finch, you probably hear about today in Life of a Feature, is a way to set up experimentation. So we load your experiments super early so that we can even do startup experiments where we say, enable this feature or not. We determine your locale. We lowered the resources. And then we go into browser main loop, main message loop start, which confusingly is not where the message loop starts. The message loop is created. It's bound to the main thread, which means now you can post tasks to the main thread through browser thread UI APIs or thread TaskRunner handle get, which if you're not familiar, that's how on the main thread you can get a TaskRunner back to the current thread and post back to yourself. So this is initialized at this point. Nothing is running yet. The queues are created. You can post to them. They're not running. Then we enter the PreCreate thread phase. PreCreate threads is where we initialize the non-thread safe read-only globals. So those are globals which are initialized once and then read from all the threads in a read-only manner. So this is where we read the command line. We initialize that. We initialize metrics and logging. And then after that, you can use the UMA and logging macros from all over the place without having to worry about thread safety, because they're initialized once, use read-only forever after. And then right after that, we create the threads. And you can see at the bottom, we already had tasks in our queues, and we started running stuff right away. And this is when the fun starts. Then we enter pre-main message loop run. And since the threads are running, at least now we're doing parallelism to start the rest of the stuff. Pre-main message loop run is the last chance to do file I/O on the main thread. Ideally, we wouldn't do file I/O on the main thread, but for startup, we kind of have no choice because a bunch of stuff needs to know what to do in order to start, and all of that is saved to disk, so we have to do file I/O at the beginning. For example, we have to load your profile so that we know what your extensions are, and we need to load your extensions because those can affect the navigation. So the first navigation will ask the extension, am I allowed to do this? Do you want to redirect? Because your extensions are allowed to do crazy things. Then we load key services like history, bookmarks, and so on. Their backends, some of them are loading asynchronously. And since we have threads, things are kicking off in parallel. And at last, there on the right, we invoke startup browser creator start. What that does is it's in charge of figuring out which tabs it should open. Because at this point, you don't have anything open yet. This is all happening on the CPU. You don't actually have a Chrome window. And then it's figuring out which tabs to open. So maybe it restores a previous session. Maybe it launches URLs you provided on the command line. Maybe the policy engine from an enterprise policy is telling it always open my enterprise page, and so on. This is like a 5,000-line class you probably never want to dig in there. There's so many rules on what to open. All right, so yesterday in Jamstock, we learned, so if you noticed, all of the steps there were browser main loop. Browser main loop is the core content bit that tells us that does all of these phases. If we remember from John's talk, content is source/content is the core code needed to render a page using a multiprocess sandbox browser. Specifically, it is not Chrome. It is not aware of source/Chrome. So things like profiles and extensions are Chrome concepts. So how does content initialization manage to initialize Chrome concepts if it doesn't know about them? And the way this is done is browser MainParts. Browser MainParts is a virtual class in content, and the embedder, in Chrome's case, source/Chrome, will override that API. In Chrome, this is Chrome browser MainParts, which will override the pre-create threads and pre-main message loop run, and content will give a chance to its delegate to effectively intercept all of those phases and do something if it cares. Chrome itself also has Chrome browser main ExtraParts because Chrome has many subcomponents that also want to hook in these initialization phases. So here we have platform-specific stuff. So we have Chrome browser main ExtraParts Win and Linux and Mac. And we also have like things like X11 and views and metrics. So a bunch of subcomponents have their own extra parts and hook in those phases. So for example, before going into browser main loop, the foo phase, we will go into a virtual dispatch to browser main parts pre-foo, which will, in our case, land in Chrome browser main parts pre-foo, which will also do a virtual dispatch to all of the extra parts as pre-foo. So if you see those in the code base, don't get too confused. This is how this is happening. So now we're at runtime, and I'm going to go into the in-process paradigms, how we like to do things in Chrome. The goal number one is to remain responsive, which means we never, ever block the UI and the I/O threads. Locks and synchronization primitives are not used in Chrome, except in low-level things like the scheduler and so on. File I/O and waits, like waitable events, are banned on most threads. So if you try to use those and on threads where you're not allowed, you're going to hit asserts. You're going to try to do something, and it's going to say assert blocking allowed here. And if you're on the main thread, it's going to decheck in a decheck build. Base sync primitives allowed is similar. So how do we do lock-free, effectively, parallel programming in Chrome? So the majority of C++ classes in Chrome are not thread safe by design. So the way this works is that a class instance is typically bound to a single execution sequence, and all the tasks meant to be posted to it are sent to that sequence. So then a sequence you can think of as effectively a user thread. So it's not a physical thread, but the Chrome low-level bits, like the TaskScheduler, will make sure to organize your tasks in a way that it might hop threads, but the tasks are going to be sequential, and there's going to be memory barriers in between, so you're always going to see the effect of a previous task. Effectively, you don't have to worry about this. Things are going to be sequential. You don't have to do thread safety. Note that things like browser thread UI and browser thread IO are physical threads. A thread is a sequence that happens to be bound to one physical thread. So in Chrome, we have base SequencedTaskRunner, which is going to be the sequence, and we have base single thread TaskRunner, which also is a SequencedTaskRunner. So it's just a more specific version of it. Again, synchronous I/O is not allowed, so you couldn't do a thing like if you're on the main thread, someone's typing in the Omnibox, and you want to add history items to the Omnibox dropdown. You couldn't do something like add history items to Omnibox dropdown, get history items from disk synchronously. So instead, what we do in Chrome is we have the post task and reply paradigm all over the place. So instead, you would do something like base post task and reply with result. You provide some traits. I won't go in details into task traits, but you can read the documentation. And then in this case, you say I want to run a task that is allowed to block, perform file I/O. This task is going to get history items from disk, and the result is going to be returned to the added history items to Omnibox dropdown method. So then you avoid blocking. Everything is asynchronous. In practice, this was a simple example. In practice, the history service in this case would be a bit more complex. So you, instead of telling it where to run, you would just ask it to get the history items with what we call a continuation callback. So in this case, you say, get the history items. However you end up doing that is not my problem. When you're done, invoke this callback with the result. How do you build such a class? So what you want is, say you're building this service. You're building service A, which is bound to the main thread. You want to have a backend for your service. Your backend B is going to be bound to a private SequencedTaskRunner. I want my own sequence. Again, neither of them handles thread safety. They're running on their own sequences. And you can even use base sequence checker to make sure that this is happening. So sequence checker in assert builds is going to throw if you're using it wrong. So the way you do this is in your service, you're going to just initialize your backend task runner with base create sequence task runner with traits, allow it to block, and you're done. Simple as that. And we have documentation and all of that. How do we do memory management? So who says multi-threading says data races? Well, hopefully not, but it's possible. So how do we avoid data races? And the way we do this is we manage memory through bind. Bind is in its most simple form, bind is just wrapping a method and putting it in an object. It's saying when I call this callback, so at the top there, when I call lambda CB, invoke this method, and then when you run it, it just prints 4. Simple. No memory management involved. Now, if you want to bind arguments, so the difference between just a function pointer and bind is that you can also bind arguments to parameters to your method. So in this case, if foo is a class method, to invoke it, you need the first parameter of a class method is always the this pointer. So how do you invoke that? Well, say you have a class ref, and then you make a ref counted version of it, and then you bind ref foo, and you say invoke it on this pointer being ref. Because ref is ref counted, bind is automatically going to take an extra ref, and then your callback is going to be holding on to a ref. So now you have two references to this class, and when you invoke the callback forever, you're effectively just saying print 3, print 3, print 3, and this cannot use after free because you have a reference to it. But we do not like ref counting in Chrome. We try to avoid it as much as possible. How do we do this? The next slide is full of text, but I have other slides coming up after it to try to ease it on you. So don't squint too hard. All right, the weak pointer paradigm. So say you have a class, myService, and you do not want it to be ref counted because you're a good Chromium citizen. What you're going to do instead is you're going to use weak pointers. So if we look at the bottom here, we have weak pointers. So what this means is when we provide an extra pointer to someone else, to our service, we're going to make it a weak pointer, which means we still have a single owner. Everybody else that has pointer has weak pointers, and weak pointers can be invalidated. And we're going to see later how that's useful. Then you have your backend, which is also uniquely owned. So you have a unique pointer to your backend. And it has a special on-TaskRunner deleter, which is going to be bound to the backend TaskRunner. So we're going to see how that's useful as well in the sequence diagrams coming up. And the way you're going to use this is you're going to post task to the backend TaskRunner. You're going to say, do the read. You do not need to return a reference, and we'll see why. And then you say, when you're done, reply to me on the current TaskRunner on my onRead method with a weak pointer. So how does that play out in practice? In the simple case, you have a request coming in on your service, which forces you to do a read. You ask your backend to do a read on your backend TaskRunner. It's bound to the weak pointer. Your service is not destroyed, so when it's done, it posts back to you. Your service is still alive. OnRead happens. So this is the same as if we were doing ref counting, except that we didn't need to do extra ref count. So simple, everything is alive, it works. The fun part is during shutdown. So same case, we have a myService request, which forces us to do a read. While we're doing the read, shutdown happens. So we destroy myService. So we destroy myService. Because we destroyed the backend unique pointer, which had a special deleter that was bound to the other sequence, the deletion is actually going to happen on the other sequence. So this ensures that the destruction of backend is sequenced after do read. So we cannot have a use after free on do read. Good, perfect. Oh, 5 minutes already? Jeez. This is 9:20 a.m. OK. Yeah, so sorry, I was phased out by this. Now the backend do read is going to reply, because it doesn't know the service is dead. It's going to reply and say, here's your onRead. But since the weak pointer has been invalidated in the destructor, this is going to no op. And this is exactly what we want. If we had been using ref counting instead, the callback will be holding on to a reference to the service. And then when you actually want to shut down the service, you can't, because it has pending references. Then you need to have like a Boolean is shutdown true and check that in all of your methods all the time. So the weak pointer does all of that for you. No ref counting, sweet. Now, shutdown. Everything is running nice and smooth. Someone clicks the X. We have to shut down. So how do we do that? In practice, in browser main, you have main runner run. You're effectively forever in that method doing a run loop until it's quit by shutdown. And then you enter the main runner shutdown call, which means shutdown is happening on the main thread, which means the message loop cannot be pumping messages at the same time. So anything you post to browser thread UI during shutdown will not run. Just thought it would be good to know that. One of the first things we do is we join browser thread IO, which means we shut down communication, net, IPC. And then we enter TaskScheduler shutdown. I'll go a bit into more details about that. And then we enter the single threaded phase where we only have one thread left, and we tear down the rest. TaskScheduler shutdown. When you post tasks to TaskScheduler, as I said earlier, you have traits. One of those traits you can provide is task shutdown behavior. This tells the TaskScheduler what you want it to do with your task at shutdown. So if your task is block shutdown, that means TaskScheduler shutdown will not return until your task is done running. This is good for, say, writing to disk and stuff. In fact, a common mix is task priority background, task shutdown behavior, block shutdown. So you're saying, I don't care if this is delayed forever, make sure it happens before shutdown to save state to disk. Then we have task shutdown behavior skip on shutdown. This is safer. Skip on shutdown, what it will do is it will skip your task if it's not running, but if it starts to run, it will at least wait until it completes. This is safer because it prevents use after freeze, and I'll explain why after. But it still allows hangs, so if your task can run indefinitely, then it can still hang shutdown. So if your task can run indefinitely, then it should be continue on shutdown. And what that means is, even if the task is running, shutdown is going to complete and keep on going, and your thread is going to go wild on its own. This is safest against hangs, but it means your task needs to not be using any global state. Because, like I said, we're going to enter the teardown phase where we start deleting stuff. So if your task is using state that is about to be deleted, this is dangerous. So this is good for tasks that, say, are just going to read a thing which nobody else is touching. Then we don't care. We let it go wild and never coalesce it. But if it's going to use singletons and things that are about to be deleted, you need to have it skip on shutdown, where at least we wait for it if it's running. Clean shutdown is not mandatory. Chrome, all the services have to be able to recuperate from a crash at any point in time. So what we try to do in shutdown is really clean up everything, flush everything to disk so that the next startup is as best as possible. For example, we will coalesce your session, because the way we write the sessions to disk is we write a full session and then we write incremental differences. And on shutdown, we coalesce this back into a full session. But if we didn't, the startup would be able to reconstruct it just a bit slower. Then we enter the single-threaded teardown phase, which is, to be honest, vastly pointless. If you've already flushed everything to disk and all you're doing is operating on memory and freeing classes, you're effectively cleaning the carpets before burning the building. What I would like to do one day is, after TaskScheduler shutdown, just terminate process. We can't quite do this, yes, because a few things like logging and stuff need to flush and are using their destructor to do so. Please never use your destructor to do persistent work. No good. Testing. So how do we test with a task environment? In an integration test, like browser tests, it's easy. You already have everything set up when you enter your test body. In a unit test, you need to bring up the task environment if you want to use TaskScheduler and threading and so on. The way this is done is we have a scope task environment, which you put as a member of the first member of your fixture, of your test fixture, and then you effectively have threads from that point on. You can post tasks. You can ask it to run until idle. A scope task environment also provides a mock time mode, so you can, if you're using delays, you can ask it to fast forward time by 1 minute, see what happens, and so on. Hey, good. Yes, sorry, I'm supposed to do Dory. Why do we still have base bind when there's std bind? Ha, yes. So std functions, std bind are there as of C++11. The reason we still use base bind is that we prefer the memory primitives we actually built. So things like WeakPtr and the way we do ref counting and so on is we prefer our way. It's safer. We have dchecks against to make sure that you do it the Chromium way, which std bind does not provide, basically. Yes.
So you said not to do persistence work in your destructor.
Yes.
Where to do persistence work if you need to do it at shutdown?
Yes. So, okay, so
Can you repeat the question?
yes, I should repeat the question. So where, if you can't do persistent work in your destructor, where should you do it? The way this is done today is that in the teardown phase, there is effectively like a bunch of services have hooks. It's like my service shutdown, basically. And it's super ugly and mostly like a mess of who should go first and so on. But yeah, there's a place in browser MainLoop shutdown threads that everybody puts their stuff. Eventually, what I would like to do is to just have, you can observe shutdown, and then everybody that observes shutdown gets a notification. Then they can post block shutdown work, and then we enter TaskScheduler shutdown. So if you haven't posted block shutdown work, it's done, it's over. Yeah, but for now, we have this ad hoc mess, and yes. Yes, sir.
So just a comment, I guess, but there was a slide where you were showing weak pointer where the object was destroyed.
Yeah.
It's important to note that the posted work should not try to dereference the weak pointer. It's only on the thread that created the weak pointer.
Yeah. So Roger was making effectively a comment and note that weak pointer, just like the other classes in Chrome, is also not thread safe. So you can pass it around. So in this case, we passed it to our backend sequence. But you can only invalidate it and dereference it on its bound sequence. So in this case, it's passed around. When it gets back there, we check, oh, is it valid? No, it's not. But you couldn't check that from the other sequence. That's why it makes its way all the way to the sequence. And at this point, we realize we can't do it. Yes?
So you said we have like the TaskScheduler thing, like for running like the pool, worker pool of threads, and so on. No one does their own threads.
Yeah, the question is, we have the TaskScheduler and its threads. No one does their own threads. Ideally not. We still have old ones like history, threads, and sync. A few use cases need their own thread because they need specific, like audio thread is specific to have real-time priority and so on. But yes, ideally not. Ideally, you post everything to TaskScheduler. TaskScheduler should have full knowledge of what wants to run so that it can actually schedule. You can't schedule if you only know about half the work. I have a new door, yay. If posts task can execute on different physical threads. How do we preserve trace logging context? Hold on. I'm not sure I understand. Trace logging context.
Well, this is my question.
Yes, sir.
And like normally you would expect in the log like some context, like I did this, did that, task 1, task 2, task 3. If I posted like 3 tasks that are doing essentially like in sequence, how do I keep the trace? Like what happens after what? Because there are lots of other tasks happening. Like typically in other projects I've been through, you would like set something in the thread local storage, and that would be context logging context ID.
Okay, yeah, I see what you mean. So we have 2 things for that. If you do Chrome tracing, Chrome://tracing, you can trace what's happening, and then there's a top-level.flow category that will show arrows between things happening. So that's one way. The pending task class also has a backtrace category where we keep the symbols of the parent tasks. So you can see the chain if you're debugging. It's not super user-friendly, and now that we're posting a lot more tasks, we're looking to make it more user-friendly. But yeah, that's what we have right now. Time's up. Cool. Thanks.